Hi everyone, I'm Satyajit, and today we are going to discuss the longest repeating substring problem. So here are the contents. We're going to go through the problem statement. We're going to find out different approaches to solve this. The first major approach is dynamic programming, and the second one is suffix array plus LCP. So you find out the suffix array, and then you find out the longest common prefix for that suffix array. And in that also we are going to see what are the different ways to construct a suffix array and what are the different ways to calculate the LCP. So the problem statement, as we know, is to find out the longest substring within a given substring, within a given larger string, which appears at least twice. So it is pretty much a variation of the longest common substring problem, and thus we can use dynamic programming to solve this. So like Mississippi is the string given to us, and then we find out the different LCE for those, like Mississippi T1N is Mississippi the whole string, then T2N is the whole string except the first letter, which is M. So it would be Mississippi, and then from T3N would be SSS, SSI, SSI, PPI. So the naive approach to solve this is to compare every single LCE, and then we find out the longest that we can through this approach. But again, you might have guessed this is quite a tedious task, and it'll take a lot of time, and also every single computation will be very space and time intensive. So we've got several approaches which are suboptimal or optimal. So the first approach to solve this is through dynamic programming. Since we've already seen longest common substring before, and this is a variation pretty much of the longest common substring, we can solve this through dynamic programming, and the recurrence is the same, so pretty much the same. So if uh, the suffixes do not have the same value, then the LCE is 0. However, if they're the same, then we check the previous diagonal of it and we add 1 to it, and then eventually we keep track of it. Mind you, we're the main prerequisite to this is we are keeping track of all of these through a two-dimensional DP to store these values. Uh, However, the problem is we can only get O of n squared through this, which might not be the most optimal solution, which is why we need to look at alternatives for this. So novel approaches have been proposed for this for solving this problem, and the most appropriate approach that has been discussed is the suffix array plus LCP problem. So the first idea is to generate a suffix array for the given array, and then we have to find out the LCP for it. So firstly, we have to generate a suffix array by sorting all the suffixes in lexicographic order. So uh, A comes at the top, then B comes in the after A, and then C comes after that. So it is alphabetically sorted, all the suffixes, and then we have to find out these suffixes, and then we have to find out the corresponding prefixes. So to find out the corresponding prefixes in this scenario would be to calculate the LCE between two consecutive suffixes. So as it says, LCE of the suffix array at ith index and the suffix array at I plus 1th index. So this is a possible way of solving this, but again, if you're comparing it at every single step, it might not be optimal. So the first idea, the most important thing in this is how to form suffix arrays and how to compute LCP. So we're going to look at the first part of the problem, which is constructing a suffix array. So the first idea is to create a suffix array through suffix trees. So we've seen suffix trees before, and suffix trees is nothing but to try to find out different approaches to the same problem. So for banana we have the following suffix tree. So we have na, which uh, which is one of the substring. Then we have just the na. Then we have banana, which is uh, in itself just the uh, single substring. And then from a we have multiple different permutations. So we have just a, we have a and a, we have a and a and a. So these are the possible substrings. So suffix tree is a possible way. So from suffix trees we can find out the leaves, and then we can form a suffix array. So let's see how we can do that. So the first way of doing that is the Burrows-Wheeler transform. So what we do is we take the string, we place a hash or we place a dollar or anything of our choice at the end, and then we cyclically rotate it. So Mississippi is at the top, and then the uh, hash is at the end. For the next step, it is Mississippi, and then the hash is at the second last position, and then it goes to the third last position, and then the third one comes in from here. So we essentially do not care about what occurs after the hash. So Mississippi, SSI, PPI are the different substrings that we are concerned about. We're not concerned about what comes after this. So what Burrows-Wheeler transform does is it sorts every single thing by the starting element. So for example, Mississippi is the first word, but Mississippi shouldn't be coming at the top lexicographically, because M is not the first element that you would think of in this array that comes first as in the lexicographic order. So what comes at the first is I. So I follows M, then M follows S, and then M follows P, and then P follows S. So you're converting all of these to a lexicographic uh, format. So I comes at the start, then M comes in the second position, P comes after that, and S comes after that. So again, in I, if you think about it, then I P, then P. So IPPI would come before ISSI PI, and then again length also matters here. So ISSS Mississippi comes at the absolute end. Then again, all the permutations are seen here. So this suffix tree formation can be done at O of n time. Another way to achieve this is through fat pivot radix sorting, which is another way to uh, find out the lexicographic version of this suffix tree. So what you do is pretty much just take the middle element, which is S, and then everything that comes after S, which is U, T, and Z, which are after S in the lexicographic series in the alphabetical order. So those come after that, and the ones that come before it are uh, before S. So we can think of this pretty much as a variant of a three-way merge sort. So eventually you try to recursively sort all of these things. So once you find out that S is the common factor between these, you don't care about what comes after this. You're only concerned about the second indexes here. So I, A, O, and O. So A should be coming at the top, and I should be coming at the in the middle, and O at the end. So again, partitions are created inside this with respect to the second index element, and then we solve this. However, there can be problem with suffix tree formation, because again you have to access every single leaf to find out the suffix array, which might not be computationally the most ideal for us. So a new algorithm called the DC3 algorithm has been proposed, in the recent years. So so you essentially create a new string which consists of integers. So just like r of I is equal to r, then L of r is equal to the index. We're going to see more of this through an example. So if you do not understand it here, don't worry, we're going to see more of it. So firstly, we're going to construct the suffix array. So DC3, the 3 part in DC3 means we're taking the modulus of 3. So we're going to basically form triplets of every triplets of the longer substring. So if you think about Mississippi, then MIS would be the first triplet, and then SIP would be the second triplet. So we form groups of 3, and then we compute rank array just for 1 and 2, and we compute a separate rank array for 3. So if modulus of 3 is not equal to 0, those are grouped together, and if modulus of 3 is equal to 0, then those are grouped together. So R3, R6, R0, those are grouped together. But when you think about other things like R1, R2, and R4 and R5, those come under the first category. Finally, when we find out all of these things, we merge them, and merging is done through the regular merging algorithm which we've seen before in merge sort. So now we're going to look at how DC3 works. So as we've seen, T0, T1, and T2 come as the first triplet, then T3, T4, and T5 come as the second triplets. This is how we're going to check for every single combination. So just a second. All right, so T0 is the complete string, and we add the dollar markers at the end, just to make sure we don't run out of any at the end. While we approach T21, we still have $2 at the end. So that is one thing we have to take care of. Now T0 is HANN, so this entire string is T0. Now T1 is the main string, and the first index is chopped off. T2 is the first and the second index are chopped off. T4 is like the first four indexes are chopped off, and this is the string that is formed at the end. Now whatever we find here, we're going to sort it. We're going to sort it in lexicographical order. We can use the previous algorithms for that. So A is at the start, but the dollars should be at the first. Then comes the A, then the B's, then the H, and then the other letters. Again, then what we do is we find the correspondences between these. So, for example, if T15 is our so if we want to find out the correspondence for T15, then we check for